hang on, these aren't just lab curiosities, right? Confined to tiny experiments. Our sources hint that these cosmic jitters might have actually shaped the structure of the entire universe. How does that work?
Yeah, this is where it gets really mind-boggling. A remarkable prediction of inflationary cosmology. The idea that the early universe expanded incredibly fast is that the large-scale structure we see today, things like galaxies and clusters of galaxies, actually originated from the quantum fluctuations of a special energy field, the inflaton field, in that primordial, rapidly expanding universe. These tiny quantum-born density variations were stretched across the vastness of space by that inflation, becoming the seeds for basically everything we observe. So the whole cosmos might have its roots in this quantum fizz.
Wow. And what's fascinating here, too, is how our very act of observation or measurement can influence what we detect from these fluctuations. Can you explain that a bit?
Right. It depends crucially on how you look at them, so to speak. Imagine these quantum fluctuations like tiny waves. For simple things, linear operators like the electric field, they tend to be small and behave predictably, mathematically speaking, following a Gaussian distribution like gentle ripples. But if you're measuring something more complex, like the energy density, which is a quadratic operator, the probability distribution can behave differently. It can have this slowly decreasing tail. What that means is there's a surprising sort of enhanced probability of large, intense bursts of energy popping up from seemingly nowhere, which becomes really critical when you think about how they might affect gravity.
Okay, so then nothing of space is buzzing. You can have big bursts of energy, and it can even theoretically dip into negative energy. That sounds completely wild. What does this mean for energy in empty space? Can it really be negative?
Well, this does raise an important question. And yes, in quantum field theory, the expectation value of energy density can indeed be negative in some regions. Now, this isn't science fiction. It's constrained by rules called quantum inequalities, which limit how negative the energy can be and for how long it can last. For example, in some simplified spacetime models, calculations suggest you could theoretically measure negative energy density up to, say, 84% of the time, even if the overall average value is zero. It's incredibly counterintuitive from our everyday perspective, but it's mathematically possible within the framework, challenging our usual ideas about energy.